We'll pick up the recording here. What are the range of values that people are getting for the resultant? I heard a 17 meters. What else do we have? 17? 16.6? Anything else for the resultant? Now, my sig figs are terrible. Yes, is that what you were going to pick on?
I have a different degrees.
Okay, so we've got a range of values so far for the resultant, and it seems like all of you are getting a smaller number than I am. Here are the cautions with graphical vector analysis. A little change in where your pen or your pencil or your marker lands can make a big difference. I'm generally pretty good at making sure these line up because I know how significant a differences that can be. So I'll assume until you prove to me otherwise that I'm closer to the true value. I could be wrong. It's happened before. It happens plenty. But there are typically a range of values for graphical solves. So it's when we're on a test, I'm not expecting that you'll get 21 point, what would we be able to sig fig this to? 21.3 or 21.8. You might get, very often what I'll do is say a little bit on either side of my answer because I got a lot of practice doing these. So typically I will say, like here I might say, 20 to 23 if you're in that range. Because we don't typically use graphical vector analysis for real precision answers. We use it to check our algebraic answer. We use it for sort of a quick and dirty answer to arrive at a value that we think is reasonable. So this is a little bit like Fermi estimates in that way. Now, the 12 degrees north of east, what other values are people getting? 10? 9? 8? What did you guys get? You have 10? Okay. Now, the other thing is, my marker line is so fat that my marker line actually occupied the space from 10 to 13. When you're doing it with pencil, you're getting a much better level of precision. I would totally believe that this could be 10 degrees. Again, like I said, my marker line occupied a big wedge of space. Okay, questions, comments on graphical analysis of vectors? FIP quiz tomorrow on them. Okay. Let me mention one thing before we leave these. Somebody said, well, the resultant is just the hypotenuse. It often is, and the first kind of resultant that we're going to work with solving algebraically is in fact the resultant for perpendicular vectors. So I'm going to just briefly introduce this. Quickly touch these bases. I'm not sure if I touched them in the video or not, but I want to make sure that they're covered well. So when we're looking at vectors in a diagram, and you probably have figured this out relatively recently in doing your mapping for your lab, you can move a vector parallel to itself. So if you think about, and you can add them in any order, and this is directly related to the lab. If you think about maneuvering in an urban area, and many of us don't have a whole lot of opportunities to do that, but some of you will get them very soon, I'm sure, as some of you go off to college, perhaps in urban areas. Come on. So if I'm drawing a few sort of, I could cut and paste. I could copy, huh? Duh. As we look at, if we think of these as like city blocks, and we want to navigate around them, and if I am trying to get from some point here to here, does it matter, whoops, no, copy, if I go 3 blocks east and then 3 blocks north, or can I go 3 blocks north and then 3 blocks east? Can I go here and then here? Yeah. Can I go here and then here? Yeah. Can I go here and then here and then here and then here, and then here, and then here. Yeah? Doesn't matter. Doesn't matter in what order you do them. When you're adding them up, it doesn't matter if you move all of these parallel to themselves, because guess what? In the end, lo and behold, same difference. Whoops. You can move them parallel, it doesn't matter. And that's really useful when we start doing forces stuff. So it does not matter if you add them in any order. It doesn't matter if you move them parallel to themselves. Great. So the other important bits to know about vectors, and you kind of already know that you can subtract them by adding their opposite. So which groups here figured out really early? I know one of them did. Well, if we just take all the easts and subtract them from all the wests, then we get a total distance we have to move east-west. Yeah, because what is 10 meters north but negative 10 meters south? That's all that is. So 10 meters north plus negative 10 meters south means you're not going anywhere. You're just staying where you are. When we look at vectors and we multiply them by some scalar quantity, we still have a vector when we're done. So if you double your speed and your initial speed was v, you're now going 2v. If you cut your speed in half, you're now going 0.5 v. When we get into forces, we do a lot of problems where, the force on the object from this direction is twice the force on the object from that direction. Well, one is F, one is 2F. And you guys pretty much get that. I think most people come in kind of having a grip on that. When we are doing vectors, we stick with that traditional Cartesian coordinate system we've been using. X-axis is parallel to the ground, y-axis is perpendicular to the ground, just like we did in one-dimensional motion. When we get into forces, we'll start to do things where we do what's called tilting the x-axis, but we don't have to do that yet. So, oops. Jeez Louise, Moser. Okay, so when we are doing perpendicular vectors, so this is that city block problem. If you're going directly along the cardinal points of the axis, it's really easy to use the Pythagorean theorem. It is your friend. So we'll do one with that because Pythagoras is useful for getting the magnitude of the resultant. So we'll do that first, and then we'll talk about how to get angles. Okay, so if we go, and now we don't have to worry so much about scale. If I go 15 meters east, and I turn, and I go directly 5 meters north, what is my resultant? How do I find it? Well, first I'm going to draw it. Whoops, I didn't mean to keep that same color. I'm going to draw it. So I'm going to make sure I've got these labeled. So I have displacement 1 is 15 meters east. Displacement 2 is 5 meters north. My resultant is this red line. How do I find it? Pythagoras. Perpendicular vectors are easy, easy, easy to solve. So we know d1 squared plus d2 squared equals r squared, the resultant squared. So the resultant is going to be equal to the square root of d1 squared plus the square root of plus d2 squared. So let's plug in our numbers. Resultant is equal to the square root of 15 meters squared plus 5 meters squared. Yep. 15.8113883 meters. Our resultant, we want to take our sig figs. Oh shoot, you know what? Let's pretend that I wrote that better and that's 5.0. Shall we? Let's get 2 sig figs out of this, please. So our resultant would be 16 meters, but that doesn't tell us where we are. So what other thing do we need? What we're looking for is this angle here. So to start with, because this is the part of the whole heading thing that confuses people the most. So do it first. And that is, this is going to be what of what? North of east. Here's how to not screw that up. If you struggle with this, you put your writing utensil on the line you're starting on. That's your east. You're heading north from the east. And I literally draw myself a little arrow for that angle because I screw it up less that way. So how do we get that angle? Trig! So when we want to find the angle of a resultant, the thing that we most commonly use, especially with the perpendicular vectors, is tangent function, because tangent is what? Opposite over adjacent. I will put up my SOHCAHTOA posters. I don't know where they are. I'll have to make new ones, but I've always had SOHCAHTOA in my room because it helps. You know SOHCAHTOA? Okay, good. And it's just fun to sort of mutter under your breath and people think you're crazy, and I like that. So if we want to use tangent to find the resultant here, okay, so we want that angle. Here's the other thing I do to prevent myself from screwing up. Have you noticed that I do a lot of things to prevent myself from screwing up because I screw up a lot? So when I am figuring out what are my opposites and adjacents, I literally draw myself a little line. That's my opposite, and a little line with a kink in it. That's my adjacent. So the way this is expressed, we call this angle theta. And what we say is that theta is equal to the inverse tangent function, tan minus 1, of, and this would be of d2 over d1. Because d2 is our opposite, d1 is our adjacent. So theta equals inverse tangent of 5.0 meters over 15 meters. So you do second function tangent, 5 divided by 15, and close your parentheses. Who's got a raw number for me? Answer of 18.43, and I'm sure you have the same trailing digits as I do, 94882, and on and on and on. What's our final sig figged answer? 18 degrees. And so our full answer, when I ask you for a resultant in a problem like this, your full answer should be 16 meters at 18 degrees north of east. Okay? A quick word about compass. Well, we'll do that tomorrow. I'll assign the section review problems. You can get started on those. We're going to have a FIP quiz tomorrow on graphical vector construction. Okay, so assigned is page 91, the 3A problems, numbers 1 through 4.